Hello, and welcome back to the course. Today we'll look at meromorphic functions, what meromorphic functions are. This is section 5.2.4 in the book. So, a meromorphic function is a holomorphic function with poles, basically. So there's some discrete subset S of our domain U, and the function has isolated singularities at at points of this discrete set. So these are all isolated points, and these are all poles. So that's what we mean by a function being meromorphic. Now, the thing that's special about poles is that, well, I mean, what is a pole? Pole is a point where the function goes to infinity. So what we could do is we could, instead of having the codomain, where does the where is the function value? Instead of that being C, we could let it be the Riemann sphere, which is just C and infinity, and we could define the function to just be equal to infinity whenever whenever we're on a pole, right? So it's just the function, whatever it is, on u minus s, and then on s it's just equal to infinity. So then we could just, and let's just call it f again. We could just think of a function that's defined from u, from this this domain u into C infinity, right? Now, this extended f, this f going into C infinity, that's continuous, and that's for well, it's continuous everywhere except at on the points of S, just because it's holomorphic there. So I mean, it's a continuous function, and then on S, well, I mean the whole point of what what is what is a pole? It's the place where the function goes to infinity, and we've set it to infinity. And the topology on C infinity on the Riemann sphere is such that that's that's what it means, right? So it's sort of continuous by definition, right? We've defined things so that it is continuous, right? So it's actually another way of saying that the function is meromorphic. It's a function with isolated singularities. So if you set it to infinity at the isolated singularities, you get a continuous function, right? Now, it's not just continuous at P. Now, we don't quite yet, at least, have a definition of what does it mean holomorphic for a function that's valued in C infinity. I mean, if it's somewhere, if we're on u minus s, it's really valued in C. So we have a definition of holomorphicity, but at the poles, we don't know what it means to be holomorphic when the function is equal to infinity. Well, but we're basically taking this idea that the Riemann sphere at infinity, it's sort of like at any other point, right? And we have this one map 1 over z that just swaps infinity and 0, right? And really everything should kind of be the same as the neighborhood of infinity should be just like the neighborhood around 0 if we apply the mapping 1 over z. So in this case, we look at 1 over f, right? So 1 over f is actually 0, right? If we extend this, and 1 over infinity is going to be 0, right? So in this extended sense of the arithmetic, right? So then we have, so 1 over f is actually a holomorphic function near P, right? At P even, right? Like in a whole neighborhood of P. So that's what we could say, what we could use as a definition of this, what does it mean for f, this extended guy, to be holomorphic at P? If f of P is infinity, well, we would just mean that 1 over f is holomorphic. So, all right. Now, a meromorphic function with this definition of holomorphic, um, it's basically just it's a holomorphic function from U to C infinity, right? So that's, that would be another way of defining what is a meromorphic function, right? It's a function valued in the Riemann sphere that's holomorphic, right? Rather than just valued in the complex numbers, it's now valued in the Riemann sphere. Now, there's one small technicality with this. If a function is just constantly infinity, so it's not a holomorphic function with poles. It's just a thing that's just identically infinity. Is that a meromorphic function? Now, if we said a meromorphic function is the same thing as a holomorphic function valued in the Riemann sphere, yeah, I mean that's a perfectly fine holomorphic function. However, we'll in this case, we'll in this course, we'll just say no. That's not what we mean by a meromorphic function. But it's that's really in the eye of the beholder. So in that case, it is a holomorphic function from U to C infinity, but we'll say it's not a meromorphic function. When we say meromorphic function, we'll mean the thing that's given by this definition, right? So holomorphic function valued in C with isolated singularities, and the singularities are poles, all right? And so to emphasize, sometimes instead of writing, this is kind of annoying to write down. So we might just say, if we don't really care to give a name to S or something, right? We might say let F from U to C infinity be meromorphic. That will mean that there are possibly some poles, right, in U. But we really mean this thing, but it's sort of a quick way to say it. I mean, we could say let F from U to C infinity be holomorphic, except not constantly infinity. But yeah, it's that's playing too much with the with the definition. It's better probably for emphasis. Say meromorphic, just to emphasize there could be poles, right? It is really sort of a holomorphic function, except maybe poles, right? So isolated singularities with poles. All right. Now, if we have extended holomorphic functions to be valued in C infinity, they could be, the domain could be a subset of C infinity, right? We did this with LFTs before, right? Linear fractional transformations. So if U is doesn't include infinity, then it's just a subset of C, and we're done, right? So if infinity is in U, then we'll say that F is holomorphic at infinity, right? If F of 1 over Z is holomorphic at 0. So in some neighborhood of 0, it's a holomorphic function, right? That's what we mean by being holomorphic at infinity, right? So now we have a definition of what do we mean by holomorphic at on a subset of C infinity, right? On an open subset of C infinity. So LFTs by this definition, and we actually did that before, right? These are biholomorphic mappings, right? Because LFTs are holomorphic in this setting, and their inverses are LFTs. So it has an inverse that's holomorphic. So it's a biholomorphic mapping of C infinity to C infinity. So it's biholomorphic mappings of the Riemann sphere. Those are actually the automorphisms of the Riemann sphere. All right. Now, a couple of exercises. Actually 4 exercises. So first, show that a holomorphic function, so this is going to be a function with poles, but now valued in C infinity and actually being defined on C infinity. So taking the Riemann sphere to the Riemann sphere, this has at most finitely many poles and finitely many zeros, right? Now, also, such a function, it's either constant or onto. So that's another thing to prove, right? It's, if it misses 1 point, it misses everything but 1 point, right? Now, such a function is holomorphic mapping from the Riemann sphere to itself. It actually has to be rational. It has to be a polynomial divided by another polynomial, right? So polynomial over a polynomial, and you can write that in least terms, right? So you can divide out any common roots. So it's basically right. I mean, you should be able to get it from looking at the poles and the zeros of the holomorphic function. That should really give you what is that rational function. Now, finally, if it's injective, right, then show that such an f is actually an LFT, right? So meaning that is we really have the automorphism group of the Riemann sphere, right? Okay, so that's it for Meromorphic function. This was just a short lecture. So next time we're going to start looking at the residue theorem. It's one of the most important terms. I keep saying that, but it was one of the most important terms for engineers when thinking about complex analysis. One of the things that which gets applied a lot, right? It allows us to compute integrals in a very simple way by sort of doing this calculus. So that's why engineers are interested in this term, but it has lots and lots of applications. So that's what we're going to look at next time. So see you then.